Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basics, Trigonometric Functions, Concept number 22, the cotangent of 30 degrees, 45 degrees, and 60 degrees. Now, the odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a new paradigm. I want to include everyone who needs a boost in Algebra 2. And if I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I would, okay? So inbox me at memedicine@gmail.com to get your healthy dose of Algebra 2 by ordering the complete cram session beyond the trigonometry series. You have lots of peers, classmates, and colleagues who are taking Algebra 2 with you and could use a boost as well. So tell them to inbox me at memedicine@gmail.com so that they too can order the complete cram session to get their healthy dose. You'll be glad you spread the word because they'll make great study buddies. And last but not least, the concept of cramming often has a negative connotation. But what people are actually thinking of is hurrying, which is a result of fear and can consequently be destructive to your learning process. We're not hurrying here, okay? We're cramming, and there is a difference. Hurrying is jam-packing tons and tons of unorganized information into your mental DNA over a tiny amount of elapsed time, whereas cramming is taking quantum leaps in your understanding in a very short instant, okay? So let's delve into the concept of the cotangent of 30 degrees, 45 degrees, and 60. Cotangent of 30 degrees, 45 degrees, and 60 degrees. What are the exact values of the cotangent of theta when theta is equivalent to 30 degrees, 45 degrees, and 60 degrees? I'll give you a moment to think and definitely press pause if you need to. All right, so hopefully by now you were able to press pause and arrive at an answer, and if not, that's totally fine. So let's attempt this together. Before expressing the exact values of the cotangent of 30 degrees, 45 degrees, and 60 degrees, we need to first understand the concept of standard position, okay? Doing this will simplify finding any trigonometric value, not just the cotangent. And because 30 degrees, 45 degrees, and 60 degrees are all acute angles in standard position in quadrant 1, they're going to have about 7 key features. The first feature is that the vertex of each of these angles is located at the origin, which has a coordinate location of 0 in the x direction and 0 in the y direction. The ray on the positive x-axis, which is slightly bold, is called the initial side ray. The other ray that basically is the result of the termination of the growth of the angle in the counterclockwise direction is called the terminal side ray. But for our purposes, we're going to call it R for short, okay? So this is the basic concept of standard position just for the angle. But now we're going to get into the trigonometry aspects of this standard position concept. I say position, it's really difficult for me to pronounce that word correctly. All right, so for our purposes, the fourth feature that's going to take us into trigonometry is this special point P. P is going to cut this ray off right here, and we no longer have a terminal side ray, but rather we have a segment length. And now what we're going to do next, our fifth feature, is we're going to resolve this terminal side ray that we're calling R for short into its x and y units, okay? So the x coordinate, of course, is what accounts for the ray traversing in this direction by this much units. So it traverses in the horizontal direction positive x units. And when you resolve it into its y units, it rises to the level of y by such amount of units, okay? So now what you can see that you have is an imaginary right triangle, and this is the basis for finding all trigonometric functions in Algebra 2, okay? This triangle right here is what these concepts are based on. And notice that if you're in quadrants 1 and 4, and your terminal side segment, or what's now the hypotenuse, after it's shortened by the point P, if your hypotenuse terminates in quadrant 1 or quadrant 4, the x orientation or x units is going to be positive. But if this hypotenuse were to terminate in quadrants 2 or 3, the amount it traverses in the x direction would have to be negative. And the same could be said for the y coordinate of the terminal point of the hypotenuse. If that coordinate terminates in quadrant 1 or quadrant 2, it's going to be positive. But if you resolve the hypotenuse in quadrants 3 or quadrants 4, the vertical length or the y units or y coordinate value is going to be negative, okay? All right. So yeah, this is the triangle that we base our trigonometric values from. And what I also want you to note is that R is a magnitude, specifically the magnitude of the hypotenuse length. It's not a location like x and y. So this magnitude is always going to be positive because it's derived from the distance formula. Instead of d, we're going to say that r is equivalent to the square root of x squared plus y squared, okay? And the reason why this is a play on the distance formula is because the distance formula says that the distance of a particular segment length is equivalent to the square root of the difference between the final x position and the initial x position. Well, here our initial x position is 0, so we don't need to be redundant and write it here, and you square that difference. And then you're going to add the final y position minus the initial y position. But again, our initial y position is 0 because the vertex of the angle theta in standard position, which is the beginning of the hypotenuse as well, is located at 0, y, okay? So we don't need to be redundant and write 0 in. We can just say that y squared is going to be the difference. And then, yeah, that's about it, okay? All right, so the cotangent is basically the reciprocal identity of the trigonometric function, the tangent of theta, okay? And we know that the tangent of theta is the derived quotient trigonometric function. That's the result of the y-coordinate or the opposite side of with respect to the angle divided by the adjacent side with respect to the angle, okay? Therefore, if the cotangent of some particular angle, theta, in standard position is the reciprocal identity of the trigonometric function, the tangent of theta, then obviously it's going to be equivalent to the flipped fractional ratio, and you're going to get x over y, okay? All right, and you should have already memorized the tangent values for 30 degrees, 45 degrees, and 60 degrees because these are the 3 common acute angles in trigonometry. And the reason why they're acute is because they occur between the quadrantal angles 0 degrees and 90 degrees, okay? And the reason why a quadrantal angle is called such is because its terminal side segment actually terminates on an x-axis or y-axis. So let's just go through a few as an aside. Here you have the quadrantal angle 0 degrees, as I previously mentioned. Here you have 90 degrees, as I previously mentioned. Again, we're growing in the positive counterclockwise direction. So we have 180 degrees and 270 degrees. Now let's say our angle's growing in the negative clockwise direction. I know it kind of seems like mismatch that an angle grows negatively in the clockwise direction, but that's just what it is, okay? So here again, you could have a quadrantal angle of 0 degrees, negative 90 degrees, negative 180 degrees, negative 270 degrees, etc. All right? So now let's start naming our values. You should know by now that the tangent of 30 degrees is radical 3 over 3. The tangent of 45 degrees is 1. It's the result of dividing the square root of 2 by itself. And the tangent of 60 degrees is radical 3. Now, as we previously mentioned, the answer to the cotangent cofunction is just going to be the flipped fraction, or the reciprocal identity of the tangent. So when you flip the square root of 3 over 3, you actually get radical 3. And let me show you why that is. I know what you're thinking, okay, you're probably saying to yourself, Jenna, if you flip radical 3 divided by 3, you're going to get this. You're going to get 3 over the square root of 3. But since the square root of 3 is an irrational fraction that can't be evaluated without a non-repeating decimal, not an irrational fraction, but an irrational number, rather, we're going to have to rationalize the denominator by multiplying the fraction by 1. But the version of 1 that we're multiplying by is the square root of 3 divided by itself. So when we multiply a radical by itself, we're essentially squaring it and getting rid of the square roots, okay? So that's how we wind up with 3 over the square root of 3, and we have a 3 in the denominator. These 3's cancel, and that's how we wind up with an answer of radical 3, okay? Alrighty then. Next, obviously, if you flip 1, you're just going to get 1. So the cotangent of 45 degrees is also 1. And the cotangent of radical 3 is going to be radical 3 over 3. And again, this answer was arrived at by rationalizing the denominator, because when you flip the square root of 3, you're going to get 1 over radical 3. You square the denominator to get 3, and you multiply by radical 3 in the numerator. Or essentially, you're just multiplying the inverse of this by 1, or radical 3 over 3. Okay? Let me just show you that. I'm not going to say it, I'm just going to show you. So when we flip this dude, we're going to get this. 1 over radical 3. Now we have to rationalize, since we don't want an irrational number such as the square root of 3 in the denominator. That's a no-no. That's a general no-no in the world of math. And when you do that, you get a radical 3. Sorry, that's a 3 over 3. Okay? All right, so thanks for your time. And these are basically our answers for the exact values of the cotangent of 30 degrees, 45 degrees, and 60 degrees. And as you can see, a pattern that I want you to notice is that for acute angles in quadrant 1, the value of the tangent increases as the value of theta increases, but the reverse is true for the cotangent. The value of the cotangent decreases as the value of theta increases, okay? That's a nice little takeaway, like an overall summary. And intellectual comprehension of this material was not difficult at all. And after the short amount of time it takes to complete the entire Cram session, you'll be prepared to answer a battery of questions about anything in Algebra 2, okay? So inbox me at emedicine@gmail.com to order the complete Cram session. Good luck studying.